Okay. Thanks. Hello again, everyone. Yes, this is joint work with Chinmay Nirke, who is currently at IBM and moving to University of Washington in the fall. So, okay, so let me just start by like motivating. So probably people in the audience actually know, what QMA and QCMA are, but let's just motivate a little bit why we care about these classes and their separation. So, you know, we know that in quantum mechanics, like the state of an n-qubit system is actually a 2 to the n dimensional vector. So it's like this exponentiality, right? To describe the state, you need an exponential amount of information. But it's not clear that the exponential parameters are actually useful for anything. Um, and like you might contrast this to classical probability theory. Like to describe a classical random variable that has n-bit values, you also need 2 to the n parameters. Like you need to describe the whole distribution of the random variable. But like to model like a computation that takes as input like like random variables that are n bits, like you don't actually need to know all the probabilities. You can just like get a sample from the distribution and that's good enough. So there's like a sense in which this exponentiality is like not really there, or, like not really being exploited. So kind of what you might ask is like, are there examples of n-qubit states that are useful for some computational purpose where there's no short classical description that would have been just as useful, that would have been a substitute for the state? So the specific setting that we're looking at this question in is a very broad question that you could ask in many different settings, and the setting we're looking at is specifically the setting of Merlin-Arthur proof systems. So let me get into that. So okay, I should say I forgot to click the button that makes like the animations on your slide like show up in the PDF. So yeah, imagine that every bullet point appeared one at a time. Sorry about that. You can cover up your eyes. So okay, so this is again, this should be review, but just so we're all on the same page for many people, the classical complexity class Merlin-Arthur is you have a polytime machine called Arthur. He can flip random coins. He's like a BPP machine, and he wants to decide some language, and he gets help from Merlin. So Merlin is an untrusted but all-powerful prover who can send him classical bits, a polynomial number of classical bits, and then Arthur can like do some computation on those classical bits and decide whether to accept or reject. And this is a proof system, so like the idea is like if the answer to the input is yes, then there's something Merlin can tell you that will cause you to say yes with high probability, and if not, then for anything he tells you, you'll reject with high probability. So the standard like quantum analog of this class is QMA, which is you make Arthur a quantum machine and you make Merlin also quantum, like have the capability to send you quantum states. And then there's this weird kind of intermediate class between the two. So notice I made both things quantum going from MA to QMA, but you could make just one of them quantum. So the sensible way of doing that is to make Arthur quantum, but to keep Merlin's message still classical. Kind of the opposite doesn't make sense, because like if you get a quantum message and you're classical, you have to measure it, and then the same as classical. But this is not obviously the same as either QMA or MA, right? You get like a classical bit string, but then you get to process it with a quantum machine. So these classes, I guess, like we don't know the relation between any of them, but it's believed that all three are distinct. I guess we're fairly confident that QMA is different from MA, and like less confident that QCMA is different from QMA. But if they're different, what that means is that they're quantum states that Merlin can send you that are more useful than any poly-sized classical description of the state, so any polynomial-sized bit string that you could get instead. So if we could prove this, that would be like an illustration of a way that a quantum state is like really more useful than a classical string. Okay, but we obviously cannot prove this. Like as usual in complexity theory, like to separate any sort of interesting complexity classes would like imply that something that like is believed to be hopelessly difficult. So here, like QCMA and QMA both lie in between P and P space, and we don't seem to have any techniques that are up for the job of separating P from P space. So okay, we probably cannot separate these classes outright with the techniques we have. So often one turns then to things like oracle separations. If you can't separate them in the real world, can you separate them relative to some oracle? So in some sort of fantasy world where you augment the machines by the power of accessing some oracle. So here too, it turns out no separation is known with respect to the usual definition of oracle, which I'll review in a second. So that was true before our work. It's still true after our work. So in the standard orthodox definition of oracle, there is still to date no separation known between these two classes. It's a long-standing open problem to give one. What has been achieved is for sort of tweaks on the notion of oracle, for more general notions of oracle than the standard model. So the first result in this direction is this paper of Aronson and Cooperberg from 2006. So they showed that if you augment the machine by what's called a unitary oracle, so not an oracle to decide some classical language, but actually just like a black box unitary, then you can separate these two classes. Then Pfefferman and Kimmel in 2015 refined this quite a bit. So they were able to replace this sort of black box arbitrary unitary with a black box unitary that looks pretty close to a classical function, but is not exactly. So it's what we call like a distributional in-place permutation oracle. So I'll explain this in a second, precisely what it means. And then what we achieved in this work, you might ask why 2022 when this is 2024? I guess it was the end of 2022. But we did this with a distributional classical oracle. So we kept one of the caveats from the Pfefferman-Kimmel thing, but otherwise the oracle looks very close to the sort of orthodox oracles that people normally use. So, okay, that's the result in a nutshell. So then let me now go a little bit more into like the technicalities of like what is an oracle and what is the model that we're able to show a separation in. So the standard classical oracle, right? When you talk about classical oracle separations, is you imagine you have a black box that can do some computation and unit cost, and that computation is modeled by, say, just a Boolean function. So it maps x to f of x. You could have a function with a larger domain, but you can always like model that as like many Boolean functions. And so this Boolean function model is like pretty general in the classical world. In the quantum world, you know, the zeroth guess you might make is like a unitary that maps ket x to ket f of x. But as many of us have probably seen, this is not actually the right thing to do, because for a general Boolean function f, this map is not a unitary, right? If like f is not invertible, then this is not, like if f is not a permutation, then this is not a unitary. So the standard definition that people work with for the quantum version of access to a classical oracle is the following unitary. So you get an input x, you get an output register y, which you could imagine to be initialized to be the all zeros state, but you could put anything in there you want. And then on the output register, you XOR in the value of f of x. So this is actually, you know, always a unitary for any f you pick, so it's well defined. And this has the additional nice property that kind of, if you had a classical circuit for f, so you had an instantiation of the oracle, then you could automatically build use of f as well. Like you just take that circuit, run it coherently, and like uncompute the garbage bits, and this would give you an implementation of use of f. So that's like, I think, kind of the motivation for why this is the right definition of oracle. So what are these like other definitions that people have used? So as I mentioned, the Aronson-Cooperberg version was sort of the most general, was that instead of having a u sub f for a particular function, you just have a black box u that could be any unitary. In their paper, what they specifically used was a reflection about some unknown state psi. So their oracles all look like identity minus 2 psi psi. And this is, I guess, the thing that's a little dissatisfying about this is that there are a lot more like black box unitaries. So they kind of prove their separation by a counting argument, by just saying there's like so many of these hidden states that the oracle could encapsulate that there's no way that a classical Merlin could give you enough information to pick out the hidden state. And this feels a little dissatisfying because like in the real world, when you instantiate the oracle, this kind of counting argument will not really apply, because you won't have like an arbitrary state here. You'll have some state that's you know, efficiently computable, and there's fewer of those. So that's like one reason you might want to object to this type of oracle. So then what did Pfefferman and Kimmel do? So as I said, their unitary was like a more specific kind of black box unitary. So I said it was a distributional in-place permutation. Let's forget about the word distributional for a second and come back to it on the next slide. What is an in-place permutation oracle? It's just an oracle that's the unitary that implements a permutation. So it maps x to pi of x, for pi some permutation. This is closer to a Boolean function, but one thing that's like dissatisfying about this is that their lower bound proof requires that you only have access to U and no access to U inverse. Like you need to not be able to invert the permutation. In fact, their problem is sort of based on like finding properties of the pre-image of some set under the hidden permutation. And that's again like something that kind of doesn't make sense if you have an explicit circuit for U, because if you have a circuit for U, then you can just run the circuit backwards and you get U inverse. So that's like a way in which this definition is like less good than the standard definition. Okay, so now what did we do, and then what is the distributional in Pfefferman and Kimmel? So what we did is our oracle is in the format that I said is like the standard format, but with a catch, which also applies to Pfefferman and Kimmel. The catch is in where this instance f comes from, so the Boolean function that's in the oracle. So in our setting, we'll have the function f sampled from a distribution script b, but the instance of the problem is not f in particular. Like it's not an average case problem. It's the instance is specified by b. So in particular, Merlin only knows b. Like in advance, when Merlin is trying to come up with his witness to send to Arthur, Merlin knows b, but not the particular f that the oracle will choose to use at runtime for the problem. So the setting is like you specify an instance by a script b, and then Merlin is like, oh, I need to, if this is a yes instance, I need to try to convince Arthur that it's a yes instance. So I'm going to come with a proof, but my proof can only depend on script b. So then there's this proof that depends on script b, and then in the interaction, Arthur will get this proof, and then Arthur will be able to make queries to the oracle, and the oracle will pick a random f from the distribution script b and answer according to that particular f. So this is sort of forcing the constraint on Merlin that whatever proof it comes up with has to work well on sort of all the functions that are sampled from script b. It can't be tailored too precisely to a given function. So this type of thing was already done in Pfefferman and Kimmel in sort of the same way. Like their oracle was not exactly, as I wrote before, like U of x maps to pi of x for some particular permutation pi. It would sample a permutation pi at runtime from some distribution and then run that particular permutation. So this is really, I'm not saying this is like a natural model of oracle, like far from it. It's why do we make this restriction? It's essentially because it's like it lets us prove results about Merlin because it restricts the types of witnesses that Merlin can send. Like it says that Merlin's witness C depends only on the distribution B and not on the specific function f. So it's really a limitation of the proof techniques. But that's, I guess, the best we could do. Okay, so this is the model of the oracle. So now I'll tell you, so the result is sort of, okay, this is like a slightly more technical version of the claim I made earlier. There is an oracle in this model that separates QMA from QCMA. And the way we prove it is by like a query complexity kind of result that like, if you make few queries, like polynomially many queries to the oracle, and you also have a polynomial sized classical witness, then you cannot succeed in distinguishing between yes and no instances of the language we're going to define. Okay, so now we move on. I should tell you, so now I have to tell you what is the construction, like what actually is the language, like what are the things in the oracle that we're going to use to separate QMA from QCMA, and then I'll say like one or two words about the techniques of the proof. So the language, okay, is going to be the following. So the idea, let me see sort of like at a high level, what's the idea? The idea is that the oracle will encode the adjacency matrix of an exponentially large graph. And the problem will be to decide whether the given graph is in one of two cases. So we're promised, so the graph has 2 to the n vertices, and it's also a d-regular graph for d a constant. So each vertex has degree d, and d is a constant, so each edge is actually colored with a color from 1 up to d. And so you're promised that one of two cases actually holds. In the yes case, the graph has many smallish connected components. So it kind of looks like, okay, I guess this is where the animations are sort of misleading because like these edges should not have appeared, but it has like, in the yes case, it has many connected components with like no edges going between them. And each connected component is fairly large, like super polynomially large, and there's super polynomially many of them. And in the no case, the graph is fully connected. So you want to distinguish between these two cases. And in both cases, every component is highly expanding. So it's a spectral expander with some bound on the second eigenvalue. So this is the setting. And the idea is we want to claim that in the QMA world, there's a quantum state that will let you distinguish between these two cases. And in the QCMA setting, there's no classical string that would help. I should also say, what is the distribution? The distribution over graph. So now the f that I wrote down earlier, that's a particular graph. That's like the adjacency function for a particular graph. The distribution script B will be uniform over all graphs where that have the same component structure. So like where you list like which vertices are in each component, that specifies a script B, and then the graph is obtained by like taking that component structure and randomly sampling the edges in a way that's consistent with that. So the Merlin kind of knows which vertices are in which component, but it doesn't know where the edges actually are. Okay, so why is this in QMA? What's the state that would help you? So this is where kind of the spectral expansion comes in. So you can kind of think of like the ability, what is the ability to quantumly query this oracle give you? It lets you do a walk on the graph in superposition. And now the question of like, is this graph disconnected or is it a single expander? It's asking, is the second value of the second eigenvalue of the adjacency matrix 1 or much smaller than 1? Like if I'm disconnected, then each component corresponds to a 1 eigenvector, and so the second eigenvalue is 1. But if it's connected and it's an expander, then the second eigenvalue is less than 1. So we just need to estimate what this is. And so the proof that Merlin gives you in the quantum proof is just an example of an eigenvector that's orthogonal to the all ones vector that has eigenvalue 1. And you can check this by doing phase estimation on the adjacency matrix of the graph by querying the oracle. So that is the QMA protocol for solving this problem. Okay, so now why is it not in QCMA? I think I'll only say this outline. So the outline is kind of, we build on a BQP lower bound for the same problem due to Ambinus, Childs, and Liu from 2011. So this is a lower bound in the setting where you have a quantum computer but no access to Merlin. So you just want to show that you can't solve the problem on your own. And so we have to kind of boost this up to the setting where you get a witness string from Merlin. So the proof strategy is kind of, we want to like fix an algorithm that we claim solves this problem and then show that it doesn't work by kind of first hard coding a particular witness. And we know by just counting arguments that there's one witness that works for a fairly large number of graphs, and then show that this class of graphs that this one witness works for is rich enough that you can kind of apply the ACL lower bound techniques to it. So I think I'll skip this. Yeah, so like, and kind of the proof, I'll just say it kind of combines like two classic techniques in query complexity. So there's two like famous lower bound techniques. One of them is the polynomial method, which I guess we heard about earlier in the conference, which has certain strengths. Like it works very well for highly symmetric functions because it's easier. When you have symmetric functions, you can argue about polynomials in fewer variables, and those are easier to work with. And then there's another method called the adversary method, which kind of works well when you have an understanding of like the Hamming distance between yes and no instances of your problem. So we kind of use a combination of both. So we like use an adversary method to like relate one problem to another, and then that new problem is symmetric enough that we can apply the polynomial method. And I should say that the original ACL proof also uses the polynomial method. It's really kind of a refined version of the polynomial method using rational functions, and we really follow them for this part. So this part is like quite similar to their analysis. Okay, so the open questions I would say are, obviously, like, can we get rid of this annoying like distributional assumption on the oracle? Like that would be really nice. We don't have great ideas for how to do this. Some other questions, so this is things that were pointed out to us afterwards, is that really like the distributional restriction is like unnatural in the QMA versus QCMA setting, but you can view it as like really saying something more about BQP/poly versus BQP/QPoly, so a computation with advice. So the idea of advice is that you get like a string that depends not on the whole instance, but just the instance length. So it's kind of similar to here where the advice is like restricted in what it can depend on. And so there was actually a recent work of Lee, Liu, Pelikanos, and Yamakawa that showed a bunch of cool results. So they recovered actually, our result, but with a simpler proof. And they also showed sort of non-distributional separations between QMA and QCMA and BQP/poly and BQP/QPoly, but with a kind of different catch. So their catch is that the oracle could only be accessed classically. Like you can't query it in superposition. And this is like based on the Yamakawa-Zandri problem. So that's like a new technique. And so, nice question is, can we combine these ideas? So that's it, and thanks for listening.
Thank you for a great talk. Do we have any questions? If you've got questions, please come up to the mics in the middle and queue up there to ask your questions.
Hi, thanks for the great talk. So I had a question about your distributional oracle. I wanted to know if this is the same thing or generalization of randomized oracle in the way that usually in crypto, if we have the function and we want to make it a unitary oracle, and if the function is randomized, then you can like, then it won't be a unitary, but you can make it a unitary by adding that like extra randomization that it's like a maximum mixed state from the point of view of the adversary. So I don't know if these oracles are the same or how different they are.
I'm not actually sure. Yeah, I guess I've not thought too much about the random oracle model in crypto. So yeah, I don't know. It's a good question, but I don't know how related they are. Thanks.
So if you want to prove the usual oracle separation with the standard oracle, you said your problem might just work out of the box. Do we know any other candidates?
I don't think so. Okay, so one point I should mention is like this candidate, like the problem they have based on YZ, I think, at least, so they have two problems in this paper, one of which does not work out of the box. Like it seems like clearly it will not work in the non-distributional setting, but I think there's a second problem that maybe would work out of the box, or that could potentially work out of the box, but I have to check this. So that might be the second candidate, but apart from that, I don't know of any.
Thanks.
Do you have any like intuition for how you tell when a problem might work out of the box versus when it definitely won't? Like what things you look for?
Oh, I mean, I don't know actually. So like for this one, I guess the thing is like there's kind of a danger that like if the problem is like more complicated, then you might just like fail to see like what advice like Merlin could give you. So here, I don't know, like kind of it feels like very hard to imagine like what sort of convincing proof you could get that like this like big graph is disconnected because the individual components are so large that like, yeah, how do you prove that it's disconnected? So I guess that's at the level of intuition, that's like sort of all I can say, yeah.
Okay, if there are no more questions, let's thank Anand again, and we've got 5 minutes for the next speaker.